Today we are talking about data everywhere, data anthropology, quantified self, machine data, human-centered design, and more. And folks, we have quite the lineup of speakers for you all today. Let's begin today's event by saying a big thank you to Pivotal for sponsoring today's online conference and let you know that the evolution of data infrastructure is here. You could find out more by visiting Pivotal in booth 201 next week at Strata Santa Clara. Also Thursday, February 13th at 9 a.m., Kushik Das, Senior Principal Data Scientist at Pivotal, will deliver a sponsored keynote on data science and smart systems, creating the digital brain in the Mission City Room. At 10:40 on February 13th in Ballroom G, you don't want to miss the panel discussion with Steve Hirsch, Steve Jones, Sabrina Dahlgren, with moderator Jeffrey Kelly discussing Business Data Lake, an evolution in data infrastructure, and also at 4 o'clock on February 13th in the Mission City Room B, Pivotal data scientists Ian Houston, Noel Seo, and Alexander Kagoshima host a session on driving the future of smart cities, how to beat the traffic. Thank you again, Pivotal. Folks, as we begin today's online conference, we'd like to let you all know that you'd like to open the group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for today's speakers. You can also open, move, and resize any of the widgets on your widget tray. If you'd like to tweet from the Twitter widget today, you might need to give it permission to access your account. The Twitter widget will automatically append the event's hashtag to your tweet so you don't have to. And folks, today our hashtag is StrataConf, all one word. If you have any trouble with the event today, please take a look at your help widget. If you continue to have trouble, just post it in your group chat and one of our staff will help you right away. If you have choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is to close any apps that could interfere. People always ask, so we'd like you to know we are recording today's online conference and we'll have the archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Alistair Croll, your Strata Conference Chair and moderator for today's event. Hello, Alistair. Hi, Alistair. Are you there?
Sorry, I'm here. I'm mute talking to myself. Hi, everybody. Good morning, and thank you, Yasmina, for the introduction. We're thrilled to have a bunch of the speakers on today who are going to be talking with us at Strata Santa Clara next week, which is happening in the Santa Clara Convention Center and the Hyatt. It's an amazing event, really lining up to be just a packed series of talks on big data, new interfaces, and ubiquitous computing. And so we've tried to ask a few of our most in-demand and most sought-after speakers to give us a few minutes of their time to give you a taste of what's going to be there, or if for some sad reason you're not able to make it, to give you a sense of the kind of topics we're talking about. It's a varied lineup. We're trying to touch on everything from machine data to personal sort of data ethics, from hardcore data science to sort of exploratory data, and from new interfaces for design all the way through to how data is changing society. So we're going to kick things off this morning with our first speaker, Stephen Gustafson. Stephen is Dr. Gustafson is an employee at General Electric where he leads the Knowledge Discovery Lab, and he's going to be talking about the industrial internet. And in many ways, the industrial internet is sort of the Internet of Things writ large and put to real work. But there's a brain behind it, which is making that internet smarter and making all those devices able to do the wonderful things we've all been promised by science fiction movies. So I'm going to hand things over to Dr. Gustafson to talk to us about big industrial internet data. Stephen.
Hi, Alistair. Thank you very much for the introduction. I am going to speak today a little bit about some of the material I'll talk at Strata next week. And let me just start by saying that I was at a IEEE Internet of Things conference a few weeks ago in Atlanta, and really had a great time of communicating the message of what we're doing in a vision that we call the industrial internet, of taking the Internet of Things concept that has been developing and bringing it into the industrial space. And we like to think about this as kind of igniting the next industrial revolution. We're really, I think, going to change the way that very big industries work. So as Alistair says, I'm an R&D manager at the General Electric Global Research Center in upstate New York. I've been here for about 8 years, and the last couple of years it has been a very exciting. My first couple of years working as a scientist, I did an awful lot of work with NBC Universal, which was part of General Electric back then, and looking at sort of web scale data and analytics and how to manage that kind of data, and really started some of the initial research around large-scale data management, working on very early versions of Hadoop and figuring out how we can leverage that to do very large-scale, massive analytics. And so that was very exciting for me. But the last 3 years, it's been just amazing. We have started an initiative that is kind of spearheaded at our GE Software Center in the Bay Area, and really looking at how to bring the most advanced analytics and data and software across the company. And so it's been very exciting, and I'll talk a little bit about that and then finish today with some of the research that we're doing in this space. So just to kind of level set, to make sure everybody understands where I'm coming from. So we do research for all of the GE businesses, from energy management, oil and gas, power and water, transportation, aviation. You see these all have very similar things. A lot of times they're similar assets. And we also provide similar kinds of services across these in terms of making very advanced, very large machines, and then having very sophisticated services on top of that to make sure that they're performing as best as possible for our customers. We also have interesting businesses in healthcare and in GE Capital and home and business solutions. So for me personally, it's a great place to have an amazing breadth of opportunity to work. And then the people that are going to be at Strata, you already know how exciting the data and analytics space is and software, and all these industries are really trying to transform themselves using those technologies. So let me just talk a little bit about what kind of brings us here today. So everybody's aware of how the Internet revolutionized the consumer space, and we're seeing that same effect having impact on industrial businesses. It's really about two things, about information technology and how we modernize and leverage information technology across the companies. And then it's also about operational technology. So now that we have better information, we have assets connected, we start to realize the Internet of Things concepts. How do we actually use that to drive our business? And that's what I mean by operational technologies. Of course, we've been doing this as a company for over 100 years, but now let's say it's being raised to a new kind of order of magnitude. And so let's look to see what specifically I mean that's kind of driving this stuff. So it's really about large-scale data. That's the thing that's really transforming everything. Analytics and software are going to be there to perform lots of very critical things there, but data is the thing that's been really kind of instrumental behind it. If we compare it to other sectors like government and financial services, industrial data is very different. Its creation and use are much more rapid and fast. Safety is extremely critical, and security is extremely critical. If we look at aviation, for example, a single GE Gen X jet engine analyzes about 5,000 data points per second, and that generates about 0.5 terabyte of data every flight. And so up until recently, a typical engine would often provide about 3 data points across a flight. And so now if we look at what we're seeing today, we're getting something that looks like this. So a lot more data. We have dozens of sensors that are collecting at high frequency. And if we just consider this, the IDC estimates only about 0.5% of the world's data is being analyzed, and that certainly translates to the industrial space. And I believe later this morning and then next week there's going to be a talk specifically about how data is in this kind of dark data state. So that's one big opportunity is we have a lot of data, but that's just the start. We have to figure out how to get some sort of meaning out of it. And really, at this point, it's very exciting for industries because whatever companies, whatever industry sectors figure out how to use this data the most effectively are going to be the ones that win. And so this brings me to my sort of next point, is with all this data in the software and analytics, the thing that's the really challenging from my point of view is how do we turn the prior knowledge that industries bring, the historical data from like aviation, and then other sort of tacit information that is used in day-to-day operations, maintenance, bring that together through real-time analytics so that we can do new things like automating different kinds of maintenance strategies, looking at how do we get insights quicker, and really developing new kinds of data management technologies as well as analytics to get insights that we haven't been able to get before. And of course, everybody on the call, I'm sure, is very familiar, and we're going to hear a lot next week also about this rise of data science and the technologies and companies and approaches and methodologies that have grown out of there. It's a whole new class of skill sets, and it's really kind of changing how we work. So I mentioned this before. We talk about the industrial internet. You can think of this as kind of Internet of Thing type of concept, but being put into operational technology in terms of trying to leverage that grid of connected devices, the data that comes off of it, apply intelligence on top of it so that we can have better control, better sensing, better maintenance, better use of equipment, and ultimately help the customers be more satisfied with the services and equipment that we produce. And so these are some of the components that we kind of envision in this industrial internet. So equipment, industrial data systems, analytics, having remote good user experience, data visualization, and then really kind of bringing it all back to the physical and the human networks. So in some ways, I'm coming from an AI background. It used to be about how to replace people doing jobs with automation AI. This, I think, is much more about how do we get more intelligent data, more intelligent decisions to people and enable people to be more effective. And I think that's a very sort of exciting message. We saw that with the consumer internet about really enabling people and classes of people. And I think we're going to see that now in the industrial space, is how do we leverage all this data, give it to people to be able to be more effective. And we like to think about this in this concept called the power of one. Often people think that in industry, the era of doing productivity gains is sort of over, that we sort of apply Lean Six Sigma and process methodologies to everything. Well, I don't think that's entirely true. We can really change things from going from something breaks and going to fix it model to really doing a much better job about predicting and preventing outages. And so we like to think about how do we identify when a machine or an asset or a service is going to fail and get there before it actually fails so that we can do any kind of mitigation that's possible. And it's actually amazing when you kind of roll up some of these numbers. A 1% savings in fuel efficiency of a power gas turbine, for example, over 15 years on our fleet, it represents about $66 billion in savings that would be shared with customers. And that's just in one small part of where we work. So you can get a sense of the magnitude of the opportunity and thus the amount of work and the scale of things that are going on in the industrial space right now. And so let me give another example. So if we look at a wind farm, let's start with, that produces about every second 150,000 data points to integrate that farm into the 400 megawatt grid. If we look at a gas turbine, it can generate about 500 gigabytes per day of normal operation. And that's about as much data in 300 days as all the content found in the Library of Congress. So it's immense. Previously, we'd find ways to sample this sort of data and get some sort of insight out of it. Now we're looking for new ways to leverage this information. And already, especially the example I just mentioned about a wind farm, the wind business over the last 5 years have been building products that already use on the order of about 150 different kinds of rules in software working on data to identify the best fix for wind turbine operations. So this vision has been developing over the last several years, and it's well on its path, and we're very excited to be growing with it. So I'm going to go really quickly here because I think I'm taking a little bit more time than I was supposed to. I would just make this one point here is when we talk about big industrial data, it's very different from other types of big data. It's not social network data. It's not web data. There is unstructured data in there for sure, and I do lots of research in that space. But predominantly, we're talking about sensor data, temperature measurements, different kinds of pressure measurements, vibration measurements, all kinds of streaming sensor type of data. And that really makes it an exciting place for me and my team because we're all about doing applied research and taking what's out there in the industry or in the commercial, figuring out how to make it innovative and useful for our industries. And so right now we have a lot of big data, a lot of data science technologies, but very few of them are customized for this very unique space that we're working in. So let me jump to my last slide. Okay, so let me jump to this slide just to finish with a kind of a teaser about some of the things I'll present next week. We'll be talking about 4 or 5 different case studies of research programs that we've done that looks at taking big data technologies, data science type of enabling technologies, and innovating them for the industrial internet vision and helping to make that a real thing for our customers. So this is an example that we started working on a few years ago. We have a business called GE Intelligent Platforms that has a very good historian database. And the challenge at that time was how do we take this and scale it horizontally so that we can do queries that would take us 6 hours, do it in 20 minutes, or take a query that could go in 20 minutes and do it in a minute. And how do we look at instead of looking at from several weeks or months of data, look at 10 years of data across all the assets. And so what we did was, back in the early days of Hadoop, is to leverage Hadoop, build some unique technologies around job management, query planning, and user interfaces, as well as working with different proprietary formats to figure out how do we use that technology. And the R&D went very successfully, over 15 patents filed, very good performance, and right now it's being sold on the market as GE Intelligent Prophecy HD solution. And so we're very excited to be able to have the opportunity to do this kind of work. And next week I'll talk about several other examples. So I thank you very much for your listening today. For people who've already reached out, I've really enjoyed the conversations, and I look forward to talking again next week and meeting many more of you. Thank you.
Cool, Stephen. Thank you very much. Looking forward to hearing more details. I want to confirm one thing which I thought was astonishing. Can you give me you said a 1% improvement in turbine efficiency represents a $66 billion savings over a 15-year lifespan?
That's right. Yep.
And that's for that turbine or for all the turbines in the world? Give me some more context on that number.
For the industry.
So if you make turbines 1% more efficient, wind turbines 1% more efficient.
That's right. So this specific example is for gas turbines.
Oh, it's for gas turbines. Okay.
Power plants. So over 15 years with our customers, which is a large share of that market, a 1% improvement is about $66 billion in savings over 15 years. And that's repeated. The similar kind of statistic in freight utilization, $27 billion, in healthcare, predictive maintenance in healthcare, $63 billion.
Those are crazy numbers. So, I mean, you can pretty easily chop off trillions of dollars just by achieving the efficiency. Do you think more of the efficiency that you're going to see, more of the productivity you're going to see at GE comes from analytics or from material science in the future?
It's going to be a mix, and I'm really glad that you brought that up, because this really isn't just about taking data off of an asset and doing prognostics or diagnostics faster or more frequently. What I'm really excited about is that it's really changing how science is done. So material science is one. Manufacturing, smart manufacturing is another. These are ways that taking software, data, and analytics are enabling people to do their science differently. Different new ways of testing hypotheses, doing it much more rapidly. And that's ultimately, I think, is going to be where we see like some of the really big fundamental shifts. Right now we're doing an awful lot around all this available data, and I think down the road we're going to see a lot more big things coming out, just like in material science. Just like another example is like with 3D printing, how that's really changing how people think about manufacturing.
Sure. Okay, we got time for one question before we move on to Monica here. So a few people in the chat room are talking about data privacy, which always comes up when we're talking about collection. Certainly there's this view of collect things just because we can, and they'll be useful later. And I know I talked to one of the guys at CERN who said that the thing that stresses him the most is he throws away 99% of the data at the sensor, and he doesn't know what he's throwing away. How do you think the balance is going to be struck between collect everything just in case it's useful and collect only what you need and that has a meaningful use in order to comply with data privacy governance?
That's a great question. It's really two questions. The first is the compliance regulation issues, and so clearly that's a very significant one, because we're talking about connecting, interfacing with things like at power plants, right? So you have to be very careful. We have a big initiative around cybersecurity, for example, that's been growing in parallel with the work I've talked about today. And then also like healthcare, we're doing lots of things with healthcare, so we also have to be very compliant. And that's one of the exciting things about GE. There's been a big culture with compliance in these spaces. The other issue is in the question is, what data do you collect? And I think this is kind of exciting to me, because I'm also working in the semantic web linked data space. And so when I think about publishing data and sharing data, one of the sort of fun things that grew as we were doing this research within the company was, because it is a company and there is this concept of profits and managing your investments and opportunity cost for investing things, is that we used to talk a few years ago about the value of like a bit. And so I think one of the things is that we're always thinking about what data should we collect, why should we collect it, what value are we going to get out of it. And I don't see a future where everything is collected. I mean, we're going to have to figure out what is valuable, and then very consciously throw away the stuff that isn't valuable. That's just going to, I think, is definitely will happen. But we're getting smarter about what is a meaningful thing to collect.
Yeah, there was a great quote by Bertrand Russell. I think it was things we know are science and things we don't know are philosophy. And we talk a lot about data science, but questions about what will be useful in the future border on data philosophy. So there's a lot of discussion to be had there. All right, thank you very much for your quick look at this. I'm sure it's going to be fascinating to see the whole thing at Strata. Up next, with no further ado, is Monica Rogati. She's been a friend of Strata and a frequent presenter there many years going, including an amazing victory at one of the events that we had done as a debate. And she's now the Vice President of Data for Jobon, and she's going to talk to us about learning from sleep data. Monica.
Good morning, everybody. Good morning. Hi, Alistair. Good to see you. I'm going to start just giving you a preview of data science for sleep, and it's just a very gentle introduction into data and sleep data and what you can get out of it. And to me, it's just very exciting because sleep is such a mystery, right? I mean, and we still don't understand it, and we spend a third of our life sleeping, and it's still such a big mystery. I'm going to start with actually going to Spain and talking about how about 18 years ago, more than 10,000 people from 110 countries donated their pictures to the Domus Museum in Spain. And, they each contributed a bit of themselves and a collection of pixels, right, their face. And you could say they contributed a bit of their data. And actually what the museum did with all that data is, Sorry. So what they've done with that data is actually make what they named the Gioconda Sapiens, and that's a face with 10,000 faces, and obviously you can see it's the Mona Lisa. And each person became a pixel in this painting, and we could literally see the bigger picture. And that's the shift that's happening today in what we now call big data. And that's a world when you see the whole picture, and it's much, much bigger than the sum of its parts. So how does that affect us? Well, today we see this world of wearables and the Internet of Things. And I believe this is the fourth mention of the Internet of Things, if anybody has a drinking game going in 20 minutes. But it's a really important topic. But at Jobon, we believe the Internet of Things is not really about things, it's about you. And it's about your environment adapting to you and really understanding you and being smart about making your life better. And how do we do that? Well, at Jobon, we start by inspiring you to be healthier. We have the app activity tracker, and we track movement, sleep, and nutrition. And the data that I'm going to talk about today is sleep. And the kind of information we can extract out of it is just absolutely fascinating. And you can see how people are living, how they interact with their devices, and so on. And there's a lot of data. It's a vast amount of data, and we have an amazing opportunity to look at the community and understand more about how we sleep and how we move and how we eat. And we can look for interesting patterns that can tell us more about the world and the lifestyle choices people make and how we're all unique but amazingly similar. And I was talking before about sleep being a black box, and it's difficult to track, and we're changing that because we can gather data at scale in authentic settings, right? So when people tell you about how they slept last night, that's actually proven to be it's notoriously inaccurate. And when you collect this at scale, you can really see the stories emerging. So how do you find them? How do you find these stories in this data? How do we zoom out and see that Mona Lisa picture? Well, that's where data scientists come in, and that's our team, data science team at Jobon, and that's us in Halloween costumes, and it might look like we're animals, but reality is we're big data technologies. There's your geeky slide of the day for you. Homework is to figure out which big data technologies we are in that picture. But our background is very varied, and it spans anywhere from computer science to astrophysics, particle physics, political science, and so on. So it's all about being technical, but also being creative with the data and finding all kinds of interesting stories. Okay, so let's take a look at them. So the first thing you can do when you kind of start looking at the data is look at hundreds of thousands of app users and look at how they sleep. And these are the kind of things you can find out. You can find out that, oh, okay, look, Vermont, it turns out to be the best rested state. You can see that Hawaii is actually where people get less sleep. I don't know if they're partying or if they're jet lagged or, but it's super interesting to see that. You can see the night owls and college students staying up late in college towns. And you can also see people that are a little bit older, the 25 to 35-year-olds staying up either to party in big cities or, Silicon Valley, being up, presumably up for work. And then this is just a very rough cut. And you can start digging deeper and finding more interesting trends and looking at things like jet lag, and how long sleep disruption lasts when you travel coast to coast. And, the one that was a lot of fun to look into for me was to do a little of a rough cut about who gets more sleep, men or women. And when I ask people about this, they say, men get more sleep. And, that's wrong. It turns out that women get 20 more minutes of sleep on average. And when I found that, I was surprised. So I looked into it. I said, okay, no, there must be a mistake. But no, it was right. And I looked at the literature, and it turns out the academic sleep community knew about this. And there are sleep studies that confirm these findings. And what turns out to happen is that these sleep studies have been done with 300 people. I traced it back to the original study, and at that scale, what you can say is, yes, there's a 20-minute difference between men and women, but if you try to dig a little bit deeper and find a little bit more in there and see, well, is location a factor? Is age a factor? Is BMI, body mass index, a factor? You can't, because there just isn't enough data to do that. But when you have hundreds of thousands of people contributing their sleep data, you can see patterns that you weren't able to see before, and you can see things that are just taking science to a whole different level. So what we've done is we graphed the sleep duration, and sorry about the non-zero based axis there. And you can graph the sleep duration and see how that varies as people age, and you can see discover things that I didn't know about before, and that we didn't know about before. Things like you have the what I call the freshman 4, which is men at age around 19 gaining an extra 4 minutes of sleep because presumably they go to college and they taste freedom. But the effect is short-lived. And then you see a narrowing of the sleep gap between men and women at 51, and that turns out so there's a hypothesis that this could be hormonal. Then you see a retirement bump at 62 for women and a 64 for men, which it turns out to be exactly the retirement age and the average retirement age in the U.S. So just very fascinating insights, and I'm going to talk about more at Strata. And to me, what's very powerful is that we can know more about ourselves and how to understand health just by looking at hundreds of thousands of data points. So I'm going to go pretty fast through these, but the Mona Lisa was not the only work of art that Da Vinci produced, and what made him more famous was being a Renaissance man. He was also an inventor and an engineer, and not only do we have individual data points adding up to a bigger story here, but what the magic happens when you combine data streams for different sources and make connections you're never able to make before. So one of the easiest ways that we can corroborate our up data with other sources of information was to survey our users about their sleeping environment and ask them about things of whether they wear socks and so on. And you can look at our Tumblr page, jobon.tumblr.com, and find out more about that. And that was still kind of small scale. If you ask users, it's not the kind of scale that we wanted to see. So what we've done next is looked at government surveys where they have about 130,000 people that they asked about very detailed habits and what they've done in the past 24 hours. It can get pretty detailed. And so there we found a bunch of interesting facts around what activities correlate with more sleep and what activities correlate with less sleep. And I'm going to talk a lot more about this at Strata, so join us there. And it just paints a very interesting picture about this kind of very relaxed, outdoorsy life where you get more sleep, and the more stressful urban life where you get less sleep. And it's just things that we weren't able to see before. Another one of these stories that we've done is to look at what people actually lost sleep over last year, right? So you can see on Twitter and Facebook, you can see what people talked about, but what we can see is what actually people cared about enough to lose sleep over, literally. And it turns out that it wasn't Miley Cyrus. It was more about the Boston Marathon keeping people up, and the Super Bowl, and a lot of events that really affected people, and either kept them up partying or kept them up worrying. And now that we've seen the Mona Lisa, right, let's zoom back into the individual and see how do we motivate you to empower, and how do we empower you to be your best, right? Let's see how we can turn these art and insights into reality. So the way we do that is to take these explorations and give the data back to you in the form of a deeply personalized experience. And even when we don't know a lot about you, we have the experience of seeing what worked and what didn't work for people like you. And maybe we see that people like you have a hard time sleeping after a big meal, or maybe you exercise before bedtime and that doesn't go so well. And you can look at how do you respond to an encouraging tone or a drill sergeant. It's all about what we call data products, and taking that data and giving it back to the user in the form of very personalized experiences. And if we do it right, all of this is happening behind the scenes, and they're very sophisticated algorithms that just enable that experience, and the deeply personalized experience that you can that can make your life better. And that's because we believe that data science is not about giving you charts and graphs, but it's about empowering you to be your best. So with that, I encourage you to come next week and see my talk. I have a couple more data stories in there for you, and one of them is about sports, and you'll get to see how people work out, and that's what we're going to go over next week.
Awesome. Thanks, Monica. I have a couple of quick questions. There's a whole bunch of questions in the chat room about correlations and analysis of this stuff that I think underscores the bigger question of, wow, there's a lot of data here, and once we figure out how to correlate all these things, we can really improve society and people. Obviously, you're dealing with a large amount of data, but relatively small and uncontrolled in this case. You don't know things like this person was on an airplane or this person just had an argument. But as sensors get more advanced, I guess the question I'd like to ask behind all this is, what are the implications of personal life logging and digital sensing on the digital divide? And I guess the example I would put forward is when the bump map application came out in the city of Boston, smartphones were used to detect where there were potholes. And they massively overreported potholes in poor neighborhoods because the poor neighborhoods, the rich neighborhoods, they massively overreported rich neighborhoods because rich neighborhoods had people with unlimited data plans and phones that could be left on all day that were high-end smartphones. So as you start to use this data to inform public policy and we start to learn things, how do we control for the idea that the data is not a sample of all people, but rather those people who are rich enough to avoid the latest cutting-edge wristband and so on?
Yeah, to me, that's very interesting because it's true that the early adopters are going to be overrepresented in this data, and to me, it's very important to take this early adopter data and learn things that we can apply that inform policymaking and society overall, and it's going to be very interesting how this shakes out, but I think these lessons, we can understand how to apply them more broadly as the data grows, right? So initially, it might be early adopters, and I was in the early days at LinkedIn when we only had, I was at LinkedIn before, and we only had 20 million users. And this is exactly the same type of caveat that we had to look into and say, hey, what we're learning now, it's about a select group of people, and we have to keep that in mind. And that's true as sensors become more ubiquitous and become more skewed towards a certain type of the population. But as the sensors grow and they become more widespread, that picture is changing, right? So we have now on LinkedIn, there's 300 million people. I don't know what the official number is anymore, but it really is no longer about a particular subset of early adopters. And what I'm seeing is that the growth in sensors is going to be it's going to happen even faster, right? It's going to accelerate, and it doesn't have to be that people can afford people who can afford the latest gadget. It can be sensor data that we gathered at the society level, right? So there's a lot of sensors that can measure traffic and can measure, there's satellites that you can look at traffic patterns and grocery store parking lots, and that data can be we have a lot more control over what we see there and how we can focus our attention towards areas that might be otherwise underserved.
Yeah, that's an interesting topic. The idea of can London turn all its CCTVs into a measurement of physical activity by citizens and stuff. Well, we're running out of time on this session, but it's going to be fascinating to hear the rest of this in person. Thank you so much for sharing some of it with us. And if you look at the chat room, there are literally dozens of people who want to ask you more questions about where your data came from. Without too much further delay, we're going to get to Dean Malmgren. Dean is a co-founder and the managing partner of Datascope Analytics. He is going to talk to us about the other side of data science, which is really how to think about design. It's more than just storing and generating reports and stuff, but actually thinking about designing data-oriented projects and communicating information properly. He's going to do this as a sort of workshop format at Strata, but he's going to give us a sneak peek into it now. Dean.
Well, thanks for the introduction, Alistair, and thanks for organizing this. It was kind of fun to get on the line with some other people and share some ideas about what's coming up. As Alistair mentioned, I'm one of the co-founders of Datascope Analytics, which is a data science consulting firm that really specializes in using the design process to solve problems in useful ways with data. And that's kind of a mouthful, but I think the basic idea is that we take a lot of pride in doing the right thing, and we've learned from designers quite a bit over the last few years about how to use the design process and design thinking in solving problems, and that's kind of what I'd like to share with you today. So on behalf of Mike and Lori, who are co-presenting with me at Strata, I just want to give you a little sneak peek on what this looks like. So if you take anything away from this short intro, I hope you appreciate why the design process is so vital to solving problems with data. And it has a lot to do with ambiguity, actually. And so I'd like to kind of walk through this sort of toy set of problems to illustrate my point. So if you can imagine, there are a whole suite of problems that quote-unquote data scientists can solve. One of them might be something like take the sum of two numbers or a set of numbers or a set of 10 trillion numbers, whatever it is, and report the answer to me. And if the problem were that simple, sure, there would be some question of what tools we might use. The more data that you have, if you want it to get it in a reasonable amount of time, at some point Excel stops being a useful way of doing that, or any like command line thing doesn't really work, and so you have to scale to using Hadoop. But nonetheless, as the project evolves, there's very little wiggle room in terms of how you might approach this problem. So over the course of a project, which I'm kind of representing vertically from top to bottom, you might not change your approach very much in solving that problem. But as you start to explore more challenging problems, even something as simple as like a linear equation, your approach could change depending on lots of things. For example, whether or not the matrix A is invertible. So this is like really nerdy illustration to get to the point that there is quite a bit of things, different approaches that you could do if that were the problem that you could write down. But often our problems as data scientists are much more complicated than just solving some set of equations or taking the sums. Sometimes it might be something like a linear programming thing where you have to optimize a set of equations subject to some constraints, or something even more complicated where you have a nonlinear optimization. But regardless of whether you end up having some problem like this, there's actually an equation that you can solve if you were a data scientist working on something like this. What I claim, though, is that the vast majority of problems that we tend to solve as data scientists are much more ambiguous and can't be written down necessarily as an equation. It might be something like optimize our profitability. And in these situations, it's very difficult to know what you should do first and why that approach is the right approach to do in the first place. So at least in my experience, these are the types of problems that we tend to face quite a bit at Datascope Analytics, and I'm sure that other data scientists have also seen. And so the question is how to approach this in some sort of a systematic way. But before I get to that, I kind of want to touch on where this ambiguity or where this wiggly room as you go through the life cycle of the project comes from. And at least in my mind, it comes primarily from two sources. The first is that even in situations where you have very well-defined problems, for example, measuring market growth, which is that circle there on the left, even if in a situation where you have a very tangible problem to work on, there are many divergent paths that you could take to solve that problem in a reasonable way. One thing is that you could take three different data sources. You could take any number of data sources and use them to address that problem. It could be private data. You could use public data. You could use third-party data. And then you have this layer of analysis that you can do on top of that I'm illustrating in green. You could be fitting models or doing some time series analysis or networking analysis, whatever it is. And on top of that, still you have a whole layer of ways that you can summarize this information in various visualizations or even just in a table or a report, whatever it is. So as you can see, there are lots of very reasonable ways to solve this problem, and the question is, which of these paths, if any, do you want to take to address that problem? This is a big challenge, at least in my experience, and something that I think the design process is particularly well suited to address. The second major source of ambiguity, I think, is that even when, is that basically problems are often poorly defined or just unclear to begin with. And even in the situation where you have something as innocuous as identify the best location to plant new trees. Suppose you were working for a forest preserve, and this is the kind of thing that they asked you to do. They gave you the layout of their park. There's a river and a path and a few trees that exist now. But the question still is, like, how do you identify the best locations to plant new trees? Well, for one thing, it's not exactly clear what you mean by new trees. How many? What kinds of trees can I choose? Am I limited to maples, or can I use oaks or spruce trees? What are my options here? Can I move some of the old trees? Can I replace them? What does it mean to identify the new trees? The second thing is what do you mean by best location? There are any number of things that you can mean by that. Does that mean aesthetically pleasing? Does it mean to maximize growth or increase foliage in the park? Does it mean something about offsetting carbon emissions? What exactly are we trying to do here? And so depending on how you answer those questions, it's actually quite difficult to identify the right problem to solve in the first place. So the question, I think, for many of us is how can we navigate these sources of ambiguity and still develop useful solutions? And one of the things that we've learned over the past few years is that actually there's a huge community of people out there that have kind of an approach to addressing problems that are inherently ambiguous. And I think I associate most with designers in this regard, but there are lots of other communities as well. And the basic idea behind the design process is that it's very iterative. So you might start by generating some hypotheses about the types of solutions that might be useful. Then you might build some prototypes to illustrate those hypotheses, and then you might put them in front of users to get some feedback, and then you iterate very quickly. And I want to put an emphasis on the quickly part because it severely constrains the amount of time that you can build prototyping, which I think is actually very important. So depending on, this might look very familiar to many of you, and depending on your background, you might have already seen something very similar to this. For example, we collaborate quite a bit with IDEO, which is one of the world's premier design firms, and they have described this process as human-centered design. Others in the design community talk about it as story-centered or user experience design, but the concept is all the same. The generating hypotheses part involves identifying personas and scenarios and use cases. You build device prototypes, and then you get feedback by doing qualitative surveys and interviews or focus groups, and then you just keep doing this during the course of a project. The lean startup community, if you're an entrepreneur, is about identifying the business and product requirements, building a minimum viable product, and then doing some split testing with A/B testing or something like that. Alistair can certainly talk that much more with his latest book, Lean Analytics, but at least that's a starting point. And then there's also the agile programming community, if you're more of a software developer, where you build user story cards, you write code, and then do QA or requirements churn and iterate until as your product gets better. So this process has been used in a pretty wide variety of areas, and I think the big question is how do we apply the same process to data science problems? And although I don't really have time to go into it in too much detail, I think there are at least 3 big barriers to doing this in a useful way in the data science area that I'll certainly be talking about quite a bit more during our workshop. So the first is when we're generating hypotheses, oftentimes the problem gets lost in translation. To paint with a really broad brush, data scientists don't necessarily know business speak. And so there's certainly a degree of expertise needed to learn about what the actual business problem is and translate that into a data science type of framework. So that's one significant challenge, and at least at Datascope, one of the things that we've tried to do is host ideation workshops where we have our clients or customers or whatever come into our office and actually brainstorm with us to learn very deeply and immerse ourselves in their vernacular and the problems that they're trying to solve. A second pretty big barrier to having these rapid iterations is that to many of you, so just to be clear, building a prototype in this particular case means not only doing the analysis, but it also means collecting the data, cleaning it, doing the analysis, and building some sort of way of representing the data, whether that's representing the results of your analysis, whether that's a visualization or a table, doesn't really matter. But I think many of us would take a look at that and say, I don't think that you can do that in 1 or 2 weeks, to put it nicely. If this were our rated audience, I might use stronger language. But I think the basic idea is that building these prototypes in a quick way is very challenging. And some of the things that we've done to overcome that is to treat one iteration on a prototype by just doing sketches, not unlike the drawings that I have in this presentation that are actually quite terrible, but illustrate the point perfectly. And we've also done things like using surrogate data or simulating data sets and that sort of thing to make it faster to get the data that we need to test our approach. The third thing, and I think that this is actually the most important point, is that in order for somebody to actually act on an analysis, we actually need to know that we can trust it in the first place. And unfortunately, you can't trust an analysis in the same way that you can when you're designing an app on your phone, and you can show somebody a set of wireframes that illustrate how it works. When you're solving problems with data, while the wireframes do get you so far, they don't actually convince you that it's going to work until you see it working on live data. I think that is certainly a point that can be debated, but I get the feeling that that's at least the case from my experience. So I'd love to continue that conversation another time maybe. And actually, just to continue the Internet of Things drinking game, as Monica started, one of the interesting things about this proof is in the pudding point is that I think oftentimes, especially as the Internet of Things becomes bigger and more pervasive, more often than not, data scientists are going to have the opportunity to design the data assets that they want to use or need to use in their analysis in the first place. And so that adds another layer of complexity in this prototyping environment, but it also has the potential to be much more valuable. So that's all I have time for today, but I'd like to thank everybody for hopping on and giving us a listen. And just to summarize, if you take any of this to heart, I hope that you appreciate that solving ambiguous problems benefits from an iterative approach. And if you'd like to learn more, I put together a couple of links in this Bitly bundle. I'd be happy to talk on Twitter, at Strata, or over email, whatever's the most convenient for you. So looking forward to it. Thanks.
Thanks, Dean. Maybe one quick question before we move on to Feline. Can you tell me a little about can you go in a little more detail about what you mean by ambiguity? Where do you see the most common sources of, if the key is to ask the right questions, where do you see where people are most often confused about what they really want?
That's a good question. I think that it most often comes from not having a well-defined problem. That sounds really negative, but what I mean is that the problem itself is inherently not obvious. And so it might start out that you want to optimize, like it seems clear to optimize click-through rate, but when in fact click-through rate is a symptom of the bigger thing, which is to optimize profitability. And there are lots of ways that you could do that, and it doesn't necessarily have to be click-through rate. Just to use like a toy example, but at least in my experience, I think that is more often than not the biggest source of the squigglies.
Cool. So maybe we can't actually do an Internet of Things drinking game on the main stage, but I think we do need to create like some buzzword bingo for the keynotes this year, because I think 5 out of the 7 keynotes I've talked to are doing presentations around the Internet of Things or the industrial Internet in one way or another. All right, up next, thank you, Dean. Up next, our next presenter, Feline Hermans, is an assistant professor at the Delft University of Technology, and she's going to talk on a very interesting topic. She's talked about this before at other Strata events, spreadsheets. It seems like while we talk a lot about big data, most of the world's usable data is residing in something that's right there on your desktop, and they represent, as she puts it, the dark matter of big data. Feline?
Hi, Alistair. Thanks. Welcome everybody to the preview of my Strata talk about indeed spreadsheets. Many people are still talking about big data and Hadoop and very interesting things. But as Alistair already said, most companies out there they're still thinking about mini data, about the small problems they have, and in many situations these problems occur in spreadsheets. So if you're still using spreadsheets, you don't have to be ashamed or afraid, because most companies do. Actually, some research has shown that 95% of all U.S. companies still use spreadsheets for financial reporting. So that's like almost all companies are using spreadsheets. And of those spreadsheets, we have found that 50% are used to base decisions on. So people are not only making nice reports just to give to management, they're also looking at their data and they're making decisions. Decisions like, am I selling enough blue cars in France? And if I'm not selling enough blue cars in France, I'm going to do something. I'm going to buy a new marketing campaign saying blue is the new black, so that people will buy my blue car. So based on the analysis in spreadsheets, people are going to make decisions. And those spreadsheets, maybe if you've worked with spreadsheets before, you are aware that spreadsheets can sometimes stay alive for a very long time. Often they start as just a simple analysis. Oh, I'm just grabbing some data from the SAP system and I'm playing with it and I'm making a nice report. It's just for me. But after a while, you start changing things and someone else starts to use it. And the spreadsheets start to have their own life. And they're sort of a shadow administration next to, well, the real systems, the software systems you have in place. And we've looked into that and we have found that an average spreadsheet is used by no less than 12 different people during its lifetime. So it's really transferred around the company. People add data, people change formulas, and during its lifespan, this happens about 12 times, the transfer. And the spreadsheets, many of them don't have documentation. Probably you are aware of this as well if you work with spreadsheets. We have found that only 1/3 of all spreadsheets have a good manual. And then our definition of manual was pretty liberal. So if there was some sort of description in the spreadsheet saying, well, put your data here and this is what happens, we said, okay, well, that counts as a manual. And still only 1 in 3 spreadsheets have a manual. So if you combine all these data points together, so let me reiterate, the spreadsheets are very complex, they're very important to the company, decisions are based on them, yet they lack documentation and they're used by many different people. You can sort of guess that this is a situation that's going to lead to disaster. And unfortunately, it actually sometimes happens that real disasters occur. There's even a European spreadsheet risk interest group, uspreak.org, this is their website, and they collect horror stories. This is their term, not mine. They make a list of all companies or organizations that hit the news because of some sort of spreadsheet screw-up. And this list is pretty long, but I'm going to show you 3 of my favorite spreadsheet mishaps to set the tone. Here's one. Yes. Last year, or at least 2 years ago now, the London Olympics, so this is a pretty big organization, right? You would expect that an organization with, 1 billion euros in budget would have a very sophisticated IT system for keeping track of their tickets. They don't. They used spreadsheets for this, and there was a tiny mistake in one of their spreadsheets, which caused the stadium for swimming to be overbooked by 10,000 tickets. So it's not necessarily money lost yet, but it was very embarrassing. People had to come in and exchange their tickets, and they were disappointed, of course, because of a spreadsheet error. But it gets worse. Here's a university in the U.S. who lost $2.4 million in projected revenue because of a typo in spreadsheets. Someone hit the 0 with their elbow or something like that. Oops, $2.5 million lost. Here's another one, TransAlta. This is a Canadian power company. They lost $24 million because of a copy-paste error in the spreadsheet. So, pretty serious business. This is like a real problem that's affecting people. So now the question, of course, is there something we can do about this? Well, I will go in a lot of more detail about exactly what we can do in my Strata talk next week, but to give you some sort of hint of the research that I've been doing, we have took the angle that this problem with spreadsheet is really similar to the problems we've been having with software for, 10, 20, 30 years now. Software is also often lacking documentation, riddled with errors, and has a very long lifespan. So we've seen the same problems occurring in software engineering before, and we see the same problems occurring in spreadsheets now, and this is where our research is aimed. And if you look at tools that professional developers use, here you can see one on the slides, this is Visual Studio, so this is a tool to make software with. If you look at those tools have a lot of support for helping you understand your code and helping you make error-proof programs. So if you look, you see there's support for debugging your program, for testing it, for analyzing it. It's not really related to writing code, but it's related to writing good, responsible code. So if you compare that to Excel, it's not really support for that. No support for finding errors or understanding a large complex spreadsheet. There's mainly support for, making things bold and making things green. And my research is focused on helping spreadsheet users get the same type of tool support as software developers have. So let me give you one little sneak peek of one of the tools we've built to help spreadsheet users professionalize spreadsheet use. What you see here is a visualization algorithm that we have developed during my PhD project. And rectangles represent worksheets within a spreadsheet. Arrows represent the data flow between those worksheets. So you can see this is a quick overview of how your spreadsheet is structured. You can immediately see, well, there are a number of worksheets. These three, the SP1, 2, 3, they're sort of similarly structured. They play the same role in the spreadsheet. And some arrows you see are thicker than others. This means a lot of data is flowing through them. So I developed this tool in the beginning of my PhD dissertation, and after that we had people in the wild, in practice, use this tool. And what was very interesting is that not all visualizations look the same. This one, this is a pretty neat one, I would say, but some visualizations look like this. So one big fat arrow, you can hardly see it's an arrow between sheet 1 and sheet 2. Other visualizations look like this. So a lot less structured. Other visualizations look like this. Even worse, I would say. And here, the pink rectangles represent data flow outside of the spreadsheet. So what you see here is a spreadsheet linking to a lot of other data sources, other spreadsheets, and other files. So we, by looking at these visualizations, we've seen that it's not just useful for understanding purposes, so to help you understand the spreadsheet, but it's also very useful for diagnosis, because when people started to see these diagrams, they said, well, this final diagram, I don't really like it or trust the spreadsheet that's underneath of it, because, well, it's so messy, it cannot be a correct spreadsheet. So we've added support to our tool now also to diagnose a spreadsheet. Is this a good spreadsheet? Is this a bad spreadsheet? And where are the weak spots within the spreadsheet? This is mainly what my talk will be about at Strata, how exactly these tools work and how they can support spreadsheet users by helping them. So I would like to end my Strata preview with a little bit of reflection on what we can learn from the success of spreadsheets, because, well, we're in big data, and why are people still using spreadsheets? This is a very interesting question, because there are better tools out there, at least feature-wise. But if you compare those tools to spreadsheets, I would say they look sort of like this. They look like this very complex dashboard with all knobs and things and meters that are very complicated, where a spreadsheet is very easy and intuitive. And it's not just that a spreadsheet is easier than flying a plane. It's also that a plane, if you're going to fly it, requires a lot of planning. I can't just hop in my plane and fly somewhere. I have to really know what I'm doing. I have to know how to fly a plane, but also I have to call flight control and say I'm going to fly off today. So it's not just the ease of understanding that's hard. It's also the flexibility and some sort of the serendipity you have if you work with a spreadsheet. So a spreadsheet, if you compare big BI systems to flying a plane, a spreadsheet is like using a rusty old bike. I mean, it's not so quick, but it's very easy, and also I can jump on my bike right now and bike to China. I will figure out how to cross the sea if I'm at the ocean. I can start right now. I don't have to make a plan. I don't have to program anything. So this is, I think, where the power of spreadsheets comes in. It's so easy, but yeah, it's also slow, and you never know what happens with spreadsheets or bikes. So I think we really have to think about the future of BI. We have to incorporate some of the success stories of spreadsheets into new BI tools, because otherwise people will continue to bike on these type of crazy spreadsheets. Thank you.
Thanks, Fidin. Very interesting, and I love your visuals. They're wonderful. I have a couple of questions for you. The tools that you mentioned, are they available to the public today?
Yes, they are available. Actually, my university has started a spin-off company. It's called Infotron, and this company puts most of the tools that we developed during my PhD project on the market. Actually, I have one slide with
Infotron, you said?
Yes, I have some backup slides. I'm pushing this slide now. So all the analysis, the visualization, and some quality analysis, you can see it now on the screen. They're combined in a tool. It's called Perfect Excel, and it's available on the Infotron website, which is on the webcast now. We even have a special Strata thing where people can sign up and they get free analysis for free if they are Strata attendants.
Cool. And I have a dumb question for you because I see this here. What does jealousy mean to you?
Oh yeah, jealousy. Yeah, that's one of the more detailed analysis. I will go into that next week. This means that a formula is actually in a wrong worksheet. So suppose a formula is on worksheet 2, but it's using only cells from worksheet 1. Then it would be better to place this formula in worksheet 1 with all the cells that is referring to. And so we say that that formula is actually jealous of the nice cells in sheet 1. This is why we call it jealousy. This is actually a term that comes from source code smells. This is not something that we come up with.
Sounds like your project, your thesis has a good sense of humor along with your pictures.
Yes, yeah. What can I say? I'm a funny gal.
All right, good talk. Looking forward to seeing you next week. We'll lead into our next speaker now, Hadley Wickham, who is the chief scientist at RStudio. R is the lingua franca of data for many people, and nobody's better to tell us about that than Hadley.
Thanks, Alistair. So what I wanted to talk about today is how can you express yourself naturally in R. And I don't mean how you express your feelings in R, but how do you express your data analysis, and how do you do data science in R. And to me, data analysis is the process where the raw data comes in on one side and understanding, knowledge, and insight comes out on the other. And I really strongly believe if you're doing data analysis or data science every day, that you should be doing it in a programming language, and I really like R. So I'm going to tell you a little bit about that first to hopefully persuade you about why you should program and why you should use R, and then talk a little bit about some of the tools I've been working on recently to make it easier to express yourself. So why program? To me, there's really three big benefits. The first is reproducibility. This idea that Felina brought up, that the provenance is really important. It's really nice to be able to track back from your final results to the initial data and to be able to figure out exactly what you did. And the flip side of reproducibility is automation. With reproducibility is about redoing the past and the present. Automation is about planning for the future and the present. So as your data changes, you don't have to redo all of your analyses by hand. You just want to be able to click a button, rerun your script, and get the updated results. But to me, I think one of the most underrated benefits of code is that it's a tool for communication. It's not just a tool for communicating between you and the computer. It's also a really powerful tool for communicating between you and other people. And one of the reasons that's the case is that code is just plain text. And you can do anything with code that you can do with text. You can dump it in an email. You can search for the example, search for the answer on Google, or you can post a question on Stack Overflow. So code, I think, is really, really important for communication. It's much, much easier to communicate code than other complicated articles. So if you're going to program, what language do you pick? I think that there's lots of options out there, Python and Julia, even JavaScript. I particularly like R, and I like it because, to me, it provides a really good set of tools for doing data analyses. And to me, there's really four main sets of tools that you need to use in the data analysis. First of all, you need tools to tidy your data to get it out of whatever crazy format it's currently stored in to something that you could work with. Then you're going to iterate between data manipulation and data transformation visualization, and modeling. So transformation is all about doing those very basic aggregates and creating new variables. And visualization is a really useful tool for both helping you refine questions and showing you the unexpected. The downside of visualization, however, is it doesn't scale very well because a human has to look at every visualization. So to me, the flip side of visualization is model, which I take very broadly to mean statistical models and machine learning and data mining. But whenever you can make your question sufficiently precise that you can answer it with a handful of numbers or a simple algorithm, I think of that as a model. So models are great because they scale very well. You can just buy them on computers if you need to. But the downside of models is that they don't fundamentally surprise you. For example, a linear model is never going to tell you that you've got nonlinear data. So visualization surprises, but it doesn't scale. Modeling scales, but it doesn't fundamentally surprise you. And in any real analysis, you're going to be able to iterate between these tools really, really quickly, as Dean mentioned. Now, R, however, it's not the perfect language. There's no such thing. And I think one of the important limitations of R is that it's really designed to work with data and memory. And if you're working with really large data sets, this can seem like a huge problem. But I think a lot of the time, big data is a bit of a mirage. Your company might have terabytes or petabytes of data, but to answer any given question, you can normally get it down to something that fits in memory with a pretty simple set of aggregates or subsets or subsamples. And I think getting the data into memory is really, really important for the most initial and exploratory phases of an analysis because you need to be able to iterate so quickly. You need to be able to ask and answer questions in seconds, not minutes, so you can find your way to the right visualization and iterate your way to the right model. So what I want to talk about mostly is some tools I've been working on to make it easier to express yourself, to express your data analyses in R. And when thinking about that, when thinking about what the bottlenecks in the data analysis are, I think it's useful to break them down into a few pieces. So first of all, when you're doing a data analysis, you've got to think about what you want to do. You've got to figure that out. Then you need to describe whatever you want to do sufficiently precisely that the computer can understand it. In other words, you've got to program it. And then finally, the computer has to go away and do it. So I think it's really important to consider these three components because I think in most analyses, the bottleneck isn't computational, it's cognitive. You spend far more time figuring out what you want to do than you actually spend computing it. So when you're designing new tools or thinking about new tools to use, you've got to be careful. You don't want to optimize computation at the expense of cognition. So I'm going to show you a couple of R packages that I've been working on, dplyr and ggviz. I'm going to show you a little bit of R code, and hopefully, even if you've never seen any R code before, this is not going to be too hard to see what's going on. So I'm going to use a data set, which is all of the logs from all of the R packages that were downloaded from the RStudio Cranmer in 2013. So that's in total, that's about 23 million packages that was downloaded, and the data set itself takes up about 1.6 gigabytes of RAM. So it's by no means a huge data set, but it is a decent size. So what I'm going to do in this analysis, very simple analysis, is I'm going to start by taking these logs. I'm going to group them by date, and then I'm going to summarize them to look at the count, the number of total downloads, and the number of distinct IP addresses. So doing this on about 20 million observations, this takes about 2 seconds. So even if you have done the wrong summary to start off with, which in my experience you almost certainly do, you can quickly iterate to get to the right summary. So the idea of dplyr is to make this as fast as possible to do using some very efficient C++ code behind the scenes, and to also make it as easy as possible and as natural as possible to express what you want. Now, once you've got those summaries, you're not going to just look at a table of numbers. You're probably going to want to visualize them. So next I'm going to show the ggviz package. So here we're using the qviz function, which stands for quick visualization. So the most important thing for any visualization is the data set. Here are our daily downloads. So that comes first. And then next we tell ggviz we want to put the date variable on the x-axis and the number of downloads on the y-axis. And we're going to display that with a line. Now, creating a good visualization is always an iterative process. And when we look at this visualization, or when I look at this visualization, the thing that jumps out most to me is this very peaky pattern. And that's basically because people don't download as many R packages on the weekend as during the week. That's probably not that useful. Once we know that, we want to remove that from the plot. So what I'm going to do is overlay a smooth line, a smooth curve to that plot. So you'll see the code is very, very similar. I've just added a new layer, a layer of a smoother. But again, the smoother isn't quite right. I think it's probably over-smoothed the data a little bit. It's removed too much of the interesting trend along with the noise. So what I'm going to do next is something that's pretty cool that you can do with ggvis, and that is you can easily add interactive components to your plot. So here I'm going to create a slider object, which represents the slider that can go from point 1 to 1, and then I'm going to map that to the span of the smoother. So the span for this particular smoother controls how wiggly this is. So when I do that, I then get a plot that has a slider on it, and when I drag that slider, I can control the wiggliness of that line. So I'm going to drag it to be quite wiggly. I'm going to make a fairly smooth span because I think that helps illustrate the overall trend a little bit better. I think it also illustrates a nice thing with making predictions from the data. If you look at the last part of the data here, it looks like downloads are plummeting down to 0. But of course, that's just largely a reflection of the fact that in December we have Christmas and New Year's, and again, people aren't downloading so many packages on Christmas, although even if you kind of zoom in and look at Christmas Day, it's rather disturbing how many people are clearly downloading our packages on Christmas Day. So hopefully this has given you a little bit of a taste for what you can do in R and how you can, by expressing yourself naturally through code, you can do better data analysis. I'll be speaking at Strata on Thursday. I also have an office hour. Or if you're not going to Strata and you'd like to find out more, you can Google for dplyr or ggvis. You'll find the GitHub websites. You can download the code, and there's plenty of documentation. So dplyr has been released to CRAN. It's usable, and lots of people are using it currently. ggvis is still pretty experimental, but hopefully we'll have an official release out next couple of months. And finally, if you'd like to take a look at these slides offline, I've included the URL for them at the bottom. Thank you.
Great. Thanks, Hadley. Looking forward to the office hours. I know you're going to be thronged with people there, so I hope you get to all the questions. A couple of quick questions for you here. First of all, just a comment. I noticed what you were talking about here and the conversation we had earlier about sort of iterative design and designing data science seem to go arm in arm. I mean, we spent a lot of time a couple of years ago at Strata with everybody trying to define what data science was and what big data was. But this idea of iteration, where you don't really know what you're looking for, but it's the unknown unknowns you're exploring for, seems to go hand in hand with these very quick results, sort of back of the napkin interactive visualizations. You think that is this interactive exploration at the core of modern data science?
Yeah, I think I kind of think of data science as in sort of two parts. You've got that initial exploratory phase where it's a matter of refining the questions and figuring out exactly what you want to do with the data. But then there's also the sort of the production phase where you figured out what you want to do and you just want to run it day in and day out. And I think R is really, really well suited for that exploratory phase where you want to be able to iterate really quickly. You sort of don't mind playing a little bit fast and loose because it gets you to where you want to go faster. And then when you sort of move into the production phase, I think the tools you need change a little bit, and you want more documentation and more rigor.
Cool, yeah, and I think the same thing could be said of what Feline was saying about spreadsheets, that they start out as a sort of scratch pad you can explore with, but unfortunately don't graduate well. So when something graduates from R, what does it usually graduate to?
Certainly you can. You can graduate just to better R code. I think people, it's nice to be able to work in one language as much as possible. I think that is possible within R. When you do get to a certain scale, I think people will generally start to use Python and C++ and Java and so on. One thing that I've been working a lot with lately in R is RCPP, which is a package that makes it very, very easy to write C++ code and access it from R. And that really helps me kind of push how far I can stay in R because I'm calling out to a programming language that's really designed for high performance.
Got it. Cool. Well, great. Thank you for the preview. Looking forward to seeing you next week, as always. Up next, our final presenters, Cameron Hetrick from VMware and Kimberly Stedman, who has an interesting background in game development, data science, and journalism. And they're going to talk to us about something that I think doesn't get enough coverage these days, which is really the intersection of humans and data. It can be said that technology is interesting when the rubber of technology meets the road of humanity, and I think big data is certainly where that happens, and I think they've already won the award for best title of a session at Strata, Soylent Means. So Cameron and Kimberly, take it away.
Hey, can you hear me okay?
Yep.
Yeah? Okay, good. Hey, folks, I'm Kim. Cameron and I are both sick, so this might get cacophonous. All right, the name of this talk is taken from the old movie Soylent Green from the 1970s, wherein science discovers this innovative new food to feed the masses, and everybody gets super excited about it. The punchline at the end is that Soylent Green is actually made of people. As a society, we're just getting used to big data, and we're also super excited about it. But when the wrapping is all the way off this thing, this is how we'll see data, made of people. We're talking here about data anthropology, or what Cameron and I call human factors in data adoption. Yes, the dreaded human, messy, error-prone, imprecise humans. We suffuse every part of big data. Humans generate data, which is used by and for humans to achieve human goals. Each step in the analysis process involves human interpretation and all of the innate biases and errors that we bring to everything we touch. In data, our tools pose problems that are for sure hard. But the messy human problems of data are way harder. For some reason, we spend all our time talking about the former and almost no time talking about the humans that use the tools to accomplish the real work of data. The full data ecosystem is both working in tandem, and each part of that ecosystem can and does break down. So if we want data to work, to really accomplish something in the world, we need to analyze and solve both the physical and human parts together.
To ensure that the social technology of big data is profitable and is broadly and well adopted, we need to keep our eyes on the bigger picture. What is the goal with data, and what's stopping us from reaching it? In the simplest form, the goal of data science is to use data to make discoveries that lead to decisions that cause changes to drive improvements. And then once we have these discoveries, the goal is to make these decisions at scale so that we reap the benefits of these changes and improvements at a larger level and ultimately drive revenue for our companies.
So that goal might sound familiar. The goals aren't new. The human race has always used data to observe and respond to our environment. Specifically, businesses have always done it. The data just looked different before. In the past, we've done it using qualitative data, which was basically all we could get our hands on. The only thing that's changed is that now we're getting the quantitative form of data at a higher volume. So while the volume is new, the process is not new. Big data is no more or less than a powerful new form of the age-old discipline of research. That discipline includes things like one-on-one ethnographic study, surveys, market research, and intelligence gathering. Each of these techniques collects and processes data in some form and then tries to turn it into something actionable. Now, I'm a broad spectrum researcher, and I've done a little bit of every type of research. I'm here to tell you, on their own, each individual method is incomplete to the point of being functionally useless. And that includes big data. The power and the potential of research comes from intelligently combining techniques to achieve your goals. And most importantly, it comes from building organizations that know how to consume the insights they yield. That's how we make the data dream real. That's how we get actions that make better products they make money, and have an impact.
So now that we understand our goal and the role of data science plays in research, the spectrum, it is important to understand how potential investors see our industry. The Gartner Hype Cycle allows us to do just that. It visually shows the adoption and maturity of specific technologies. Potential investors can track at these technologies as they move through the 5 phases of maturity and better understand the potential risk in investing in these new industries. In 2011, big data first appears on the Gartner Hype Cycle as a technology trigger, with early proof of concepts and media attention beginning. For companies looking to invest, this means that there could be huge payoffs, but also huge risk. In 2012 and 2013, Gartner continues to keep big data into the second phase, which is called the peak of inflated expectations. This is characterized by countless articles that promote the promise of big data, with several stories about success, but also a lot of stories about failure. Some companies start investing, but many don't. The next phase of the inevitable journey to maturity is the trough of disillusionment. In this phase, we see a number of experiments decrease as other investments fail and investors become wary. Investment only continues if we as the producers meet the needs of the early adopters. This means we as data scientists have to show the value of the tools we use, not just how they allow us to access big data, but rather the value that they bring to our companies in terms of revenue growth and cost savings. And we can see this in the adoption numbers. According to Gartner's Big Data Survey done in 2013, 30% of companies have invested in big data technology, but only 8 have deployed the solutions. That means 22% of companies are still experimenting. And if these experiments don't drive value, we risk the loss of future investment.
So all technologies follow a process of societal adoption. This graph is taken from the book Diffusion of Innovation, which talks about the way that all human technologies, from linguistics to irrigation to cell phones, are adopted or rejected by society. Data science is a social technology. It's following the same process. We're at the beginning. We, the very people who attend conferences like this, are the early adopters of data. So folks, we're all on stage. We set the example for the next huge wave of adopters who are watching us to learn how and whether to do this thing. The problem with that is that the vast majority of our talks and papers are what I call data haikus, isolated findings, tools, and techniques without any broader context for how they knit together to achieve that goal of data. The goal of quantitative research, or any research, isn't finding a few associated facts in a haystack of numbers. It's about causing a massive return on our investment, which in the case of data science is substantial. So to get there, we need to start from our goal and ask, what's stopping us from reaching this? I've been interviewing a bunch of data scientists and product managers, data consumers, and decision makers, and I asked them, what's the hard part? What's stopping us from getting real value out of data? The answer is almost never our tools.
And Gartner's actually done the hard work for us behind this. And through a survey they conducted in 2013, they found the top challenges of big data and what's preventing future investment. As you can see on the graph, the number 1 and number 2 items that the challenges people are citing are determining how to get value from big data and defining a strategy. Both of these issues are directly tied to the human factors around data science, not the tools.
So in our full-length talk, we're going to present some major human factors problems in data adoption, and we're going to propose how to solve them. They include
how to hire people you can actually find today versus the never-ending search for the mythical data scientist who is all things to all people.
Next, look, each step in the analysis process, from the first data definitions to the conclusions and the actions of our decision makers, involve data passing through the buggy, gnarly mess of the computer called the human brain. We will talk about the bugs in our analytic process and how to avoid them.
We must remember that the number 1 goal for all data scientists are to return value to our company. Therefore, we must take our company's goals and translate those into metrics that motivate people's behavior to dig in deeper and to learn more.
Look, the best research in the world is useless if it doesn't lead to your company taking actions that yield results. In the final segment, we're going to talk about the research and decision-making life cycle.